In section 8.2 of the ECE 301 workbook, we consider DC steady state. Now, in saying the term steady state, I want to refer back to the voltage equation that we derived from the previous section for the capacitance. When the capacitance, remember, was wired up with a voltage source, and the initial voltage on the capacitance was 0. And what we were able to do is we were able to derive this equation here that the voltage through the capacitance as time, after the switch closes and time marches towards infinity, then what we have is that the voltage source is scaled by this function here, 1 minus e to the minus t over RC, where we did have a resistance and a capacitance in the circuit. So multiplying those out, what we have is a constant term here, right? Minus this constant times this exponential. But through time, as t goes to infinity, this is negative t over RC. RC are both positive constants. They're always positive. So therefore, this term is going to asymptotically go to 0. So it's exponentially dropping to 0. So this term is usually referred to as the transient component of the voltage. And the first part is the steady state. So initially, ultimately what's going to happen, you can see, is this term will go to 0, and then you'll be left with the voltage of the voltage source. So asymptotically, the voltage of the capacitance is going to approach that of the source ever so slightly. Maybe not exactly, but it depends on how many time constants you're going, all right? So for DC sources, the steady state currents and voltages are constant, all right? So that's the fact that this term right here was a constant term because, again, the sources that we're looking at, these independent sources, are from DC sources are always going to be constant. So if we revisit the current through a capacitance, remember this was the formula for the current through a capacitance. It's basically controlled by the voltage, all right? The rate of change of the voltage through the capacitance, okay? All right, and so if we have a constant voltage, if the voltage becomes constant and stops changing, increasing or decreasing, then there's absolutely no current. And so basically, if there's no current, your capacitance is acting like an open circuit, which means it's holding voltage across it, but there's no current flow, right? For an inductance, remember, what we do is we replace these functions. You replace the current function with the voltage function. You replace the voltage function with the current, and you have pretty much the same formula, but now voltage is controlled by the rate of change of the current because the magnetic field depends on the rate of change of the current through those coils. So, so if you have a constant current, all right, then you know you have no voltage. And so the inductance then is acting like a short circuit because in a short circuit, remember you have, we have no voltage, but we do have current flow, right? So therefore, one approach to determine what might be referred to a forced response, if you had what we call an RLC circuit, means you have all three components now. In the previous lecture, we just had resistance and capacitance. Now you have all three, okay? This is what we referred to as an RLC circuit. And we're only going to consider DC sources right now, right? So, so one approach, if you want to get the response, you want to find the voltages or currents of any of these elements when you have all three involved, is you could, because in the steady state, in other words, as you approach, as time marches towards infinity, all right, then the capacitances will act like an open circuit, okay? And your inductances will act like a short circuit, okay? Again, based on what we know is the relationships here and the fact that we have these transient components, right? So, so what we can do is kind of like we did for superposition, source transformation. We can look at how we can zero sources out, but we're just going to replace for capacitance with open circuits and inductances with short circuits in the long run, okay? And then solve for the remaining parameters that we're looking for, all right? So that's the strategy, is that we know in the steady state, all right, we know that the voltage here is going to become constant. If the voltage becomes constant, you have no current. And you can show similarly for the inductances, Once your current becomes constant, you've got no voltage, okay? All right, so as an example, all right, this is a great circuit that has everything that we've talked about in this course, all right? So you have a switch, you do have an independent DC source voltage of 10 volts, you have a 5 ohm resistance, you have a 1 Henry inductance, and you have a capacitance which will be 10 microfarads, all right? And then we actually have another resistance in parallel with it, right? So our goal in this problem is we want to determine with this DC source and when that switch is closed. So after time 0, let's say time marching towards infinity, ultimately, how much voltage will be across that capacitance, and also how much current is flowing through the inductance, okay? So that's our goal for this particular problem, right? So, so what we'll do is we're going to look at the case, and let's just make a little notation over here that as time goes to infinity, remember, what's going to happen as your capacitance is converging basically towards an open circuit, okay, and your inductance is converging towards a short circuit, okay, and we're just going to put a straight line in, right? So that's what we mean, you know, as time goes towards infinity and as you reach a steady state, this is what your inductance is effectively, okay, which means that transient term is pretty much close to 0, and so your inductance is acting nothing more than a short circuit, okay, which has and it has current but no voltage. And your again, in that in towards time goes infinity, your capacitance is basically, you know, it's got voltage across it, but it's got no current, so it's acting like an open circuit, right? So we'll start off here at the bottom. We're at the bottom of page 98, all right? And so for time, let's say much greater than time 0, and the switch is closed. So that's the goal here, is we're not really looking at what happens right after it closes. It's going to take time, take so many time constants as we've seen to get close to the asymptotic behavior. So we're just looking, you know, we'll use double greater than sizes. You know, it's significantly longer than just after the initial switch close. So then what we could draw then is we've closed the switch. So we've got we're drawing this scenario is what we're doing. So we've got our voltage source. You've closed the switch, so we'll just kind of close it there, all right? And then we have a 5 ohm resistance. If we want to, we could call that R1 just to, you know, to enumerate it. Now, what did we just say? In the steady state, what's going to happen is your inductance is going to act like a short circuit. So I'll put the node there, but I'm going to short circuit it there, so it's practically gone there. And then what we have here is the bottom here. You've got an open circuit now where the capacitance was, and again, there's voltage across that, so we'll label that as Vx. And then in parallel with it, we have a 5 ohm resistance here, and maybe I'll just call that R2, okay? So again, this is the scenario of towards a steady state, which means time is marched way past the initial point, okay? All right, so this is effectively what your circuit's acting like, is what we're saying, all right? So if that's the case, then we have no current across this open circuit, and you can see very quickly then, well, as you pass, there's no current there, so as you pass out of that 5 ohm resistance, you must go into the other one in terms of current flow. So our equivalent is just in series, so we have an RQ equivalent of R1 plus R2 is 10 ohms, okay? All right, so if we do that, then we realize, of course, that the IX current, right, that's flowing through this top node is still the same current up here, all right? Because this is acting like again, in transient part is going, you know, converging to 0, so it's reaching the steady state. This inductor is acting like a short circuit, so this current is the same current through here, all right? So IX is flowing all the way through here, all right? So therefore, with that equivalent, so if you want to, we could redraw it, but I don't think we need to redraw it because it's basically that, right? So by Ohm's law, we know that Ix has to be 10 volts over 10 ohms, which is just 1 amp, okay? It's just a very simple circuit, right? With a 10 volt source wired to a 10 ohm resistance, and there's only one current flowing through that, and it's got to be 1 amp, right? So, but remember, our goal though was to determine, okay, so that gives us Ix, which is fine. So we've gotten that component done. So that was, we've checked that off. But we do want to know what the voltage is across that open circuit, which is the steady state representation of the capacitance, all right? Well, if we realize the fact that, well, it's got to be the same, it's in parallel with a 5 ohm resistance. So if we do Ohm's law on the 5 ohm resistance over there, I'm specifically referring to R2, right? Then that voltage would have to be R2 times Ix. That's the only current you've got going. They're in series, so there's only one current. So that has to be 5 volts, okay? So what that says is as time goes to infinity, yes, you have a 10 volt independent DC source, but the voltage that's going to eventually be accumulated into your capacitance is half of it. It's going to get half of it. Explained because, well, you've got resistances and you also have another inductor there, right? So, but again, the inductor is not causing the issue, it's these resistances, they remain, okay? So the fact that you've got two of those in parallel, in series, the two resistances, you're going to end up with half of the volts of the DC source, right? So let's do another example. Again, all we're doing is replacing the inductance with a short circuit and the capacitance with an open circuit, and then resolving whatever current or voltage we're interested in, okay? So we'll move on to page 99. Okay, it's the last page of the workbook with two more examples. And here we are again with a situation with resistances, capacitance. We have a current source here, and we have an inductance as well. All right, so this is definitely RLC. These are examples of, again, RLC circuits. They have all three types, right? And our goal is to determine the steady state values of the label current voltage. In this case, what we're looking for is the voltage across the switch and the current through the 25 ohm resistance over there, right? And we're assuming that the capacitance is 2 microfarads, and it looks like we've got a 2 microhenry inductance, all right? So, and again, now this is an interesting situation because of the switch. When we draw the switch this way, notice the position of the arrow. What this says is at time 0, it's opened, okay? So let's just make a special note of that. When you see it drawn this way, it means open switch. For time, after time 0, it's open, okay? It's closed up to the fact that after that time instant, if it's 0 or whatever, we're gonna say 0, then it's open. So we're assuming the timing of the switch is at time 0 and it becomes an open switch. So yes, we can get voltage. A trick question would be, what would be the current? Well, it'd be 0. No calculation needed. But in this case, oh no, there will be voltage across the open circuit from time past time 0, right? So this is not too difficult. Remember, steady state, the steady state form of that inductance is what? That's right, that's a short circuit. And the steady state representation of the capacitance, open, right? So if this is open and this is essentially a short circuit, then if we just redraw this, all we have is a 2 amp current source, okay? Flowing through, that switch is open, so there's no current. No current, no current, short circuit, all you have is one resistance. Isn't that cool? And that's just 25, we'll just say resistance 25 ohms. That's the steady state behavior. That's what's going to happen, okay? And so if we call that VA, plus minus, right? Because there will be voltage across here. This is an open circuit, so there's no voltage here. okay? Excuse me, there's no current here. There's no current here, so we don't need to worry about that. And this is a short circuit, so whatever the voltage changes across this 25 ohm resistance is going to be the same as the voltage across that one, okay? All right, so Ohm's law, IA is 2 amps, so that VA has to be what? The current times the resistance, so that's 2 times 25, 50 volts, okay? So the transient behavior is that you'll have 50 volts across that open switch, okay, right? And because these two things would be in parallel, ultimately you will have 50 volts across the capacitance as well, okay? But and in time, all right, this would be acting like a short circuit. And again, in steady state, well, in the steady state, I should be careful. In the steady state, we already said this is an open circuit. So there is nothing, you know, it'll be an open circuit. It'll have the same voltage across from this node to this node. But it'll also be the same voltage across the 25 because that is a short circuit now. And that means there is no voltage. There's no voltage here. There's current, but there's no voltage. The voltage is here, here, and here. Okay, they're all in parallel. Okay, so last example, example 2, bottom of page 99. Another example, you can see very quickly, this is an example of an RLC circuit. This time, after time 0, close switch, right? So that's different than the previous problem. So the switch closes. Let's see what we've got here. Well, these two items are definitely in parallel. That's important. And these are not in series, all right, because you've got these, and you know that this resistance is not in parallel with that, but we're only interested in steady state values, all right? So in steady state values, all right, we're looking at the case that time is marched much past the initial closing of the switch, right? And so maybe just to annotate what things look like, right, is we know this is acting like a short circuit, this is acting like an open circuit, okay? All right, so we can redraw now, close the switch, draw the 20 volt DC source, there you go. Switch is closed, 5 ohm resistance, 10 ohm resistance coming down here. This is the I2 current. The representation is I2 current going top to bottom. This has been short circuited and we come down and I'll just go ahead and draw it. This is an open circuit, means no currents flowing there. And we have a 10 ohm resistance here, okay? So we were interested in I3, so this is still I3 current up here, right? That's important, even though I've drawn this, it's just this drawing of a short circuit is saying it's acting in the limit like a short circuit, but there's still that current, okay? So we keep that current there, right? And so we want I2 and we want I3, okay, is what we're after. And we can see immediately a couple of things, all right? So this was short circuited, so, I mean, this was open circuit here, so in terms of current flow, we have parallelism here, correct? So we've got parallelism between the 10 ohm resistances, all right? So we'll go ahead and draw an equivalent. That'll be our first equivalent. We'll say REQ1 is 10 times 10 over 10 plus 10. We've done this a lot in this class, and that, of course, is 5 ohms, right? 100 divided by 20, right? So, so again, what that says is we could redraw, we'll go ahead and redraw the circuit based on that equivalent. So you have your 20 volt DC source here. You still have the 5 ohm coming up over the top here, but we've replaced this with an equivalent. Current is still the same. Oops, I forgot to, there's the equivalent, REQ1 equal to 5 ohm, all right? This is still the same current, I2, okay, all right? Again, this is just a replacement of the fact that these two are in parallel. So this is still a representation. So the current through this equivalent is the same as the current through the 10 ohm resistance there, all right? And what we have here is another equivalent, which is obviously in series. So we'll go ahead and write, I don't know, just for the sake of argument, we'll write REQ2. They're in series, so REQ2 is 5 plus 5 equals 10 ohms, right? And we resolve this down to a single DC source and a single equivalent. We'll call it REQ2, okay? And that's 10 ohms, okay? And there's just this one current flowing through this, and let's call this one I1. It would be the same current flowing up through here, okay? So we're gonna represent in the original diagram, when you close the switch, we have the current through this 5 ohm resistance. And in that case, because these two things are serial, this would have to still be the same current, okay? Because remember, if the resulting equivalent is becoming from series, then you're keeping the same, you're keeping the representation the same current, okay? All right, so therefore, we know immediately I1 has to be 20 volts over 10 amps, which is 10 ohms, which is 2 amps, right? Okay, so we've reduced, in the steady state, we've reduced this down to just one resistance and one voltage. So Ohm's law tells us, now we know for this equivalent here, there must be 2 amps flowing, right? So what we could do is this, our goal though was to get I2 and I3 back up here, but this current through the 5 ohm resistance after the switch closes is this value now. That's what we've determined, okay? Right? Again, because this equivalent is based on these two things in series. So the current through both of them is the same thing as the current through this equivalent, right? So therefore I know it's 2 amps coming through the 5 ohm resistance. And then that is splitting two ways, isn't it? If you go back to the steady state situation here, oh my goodness, it's just splitting this way and this way. So we could use CDP, okay? So again, what was really important here was to figure out what the I1 current is, because we could see if our goal is to get those two currents, I just need to know how it splits by KCL, right? So we can use CDP here, and we know that in the case of splitting these currents here, both of them in this case go through 10 ohm resistances here. So it really doesn't matter, you know, in terms of looking at distributions. The neighbor is also 10 ohms, so it's 10 over 10 plus 10, the fraction, okay, which is just a half, and we're splitting out that current, which is I1, which is 2 amps, and so that's 1/2 times 2, which is 1 amp. And you automatically know that I3 is the same thing, right? Because its neighbor resistance is still 10, okay? So it's actually the same result. So that's not too surprising. If the resistant values are the same and you're splitting it this way, CDP tells us it's split evenly then, okay? Because my neighbor has the same resistance values as I do, okay, in terms of the resistances. So what's happening in the steady state is you're going to end up getting 1 amp across this 10 ohm resistance, and you're going to get 1 amp across that 10 ohm resistance, right? And again, if we wanted, oh, excuse me, I should have read that. It's I3. Yeah, we've got the by getting the resistance to the 10 ohm, it's the same in the steady state. It's the same current flowing through the inductor. Be careful what I was saying, because in the steady state there is no current flowing through here, but there is current flowing through this inductor, which is acting like a short circuit. So again, when we talk about steady state, even though we represent it as a short circuit, it's still the same current that flows through the inductor, right? Very, very important. Same thing with the voltage across the capacitance, okay? Yes, in the steady state, this acts like an open circuit, but there is voltage across it, because there's voltage across an open circuit, just like there's always going to be a current across a short circuit, okay? So those are some examples of RLC. All we have to do is put in the behavior and basically end up doing our network analysis the way we have before, using CDP, using whatever techniques we want to use, NVA, net voltage analysis, superposition, whatever it is that makes sense for the problem, because it's just resulting back to a problem that we've solved before, right? But it's a representation of what happens as time marches towards infinity.